Hey everyone, welcome to Zero Labs. Today is Monday, March 9, 2015. I'm Mark Brash, your host, and finally we get into the review of the 3D printer from Have It Shop on eBay. This is the Prusa, the RepRap Prusa i3 A600 or H600, not sure which. There's sort of a little discrepancy there. 3D printer. So, in no particular order, here are some of the things that I dislike about this kit, and some of the things that I really like about this kit. One of the things that I learned very quickly about the calibration of this particular printer is that it is very heavily dependent on the surface that you place it on. This is true of pretty much any open frame 3D printer that you will buy on the market. All right. The reason for that is because you have generally 4 points of contact. This one really has 6 points of contact, but that's kind of debatable depending on how flat your surface is. Anyway, one of the very critical adjustments is the height of the Z-axis when it goes to the home position above the moving plate, all right, above the hotbed. The head, the nozzle, has to come to rest at a very specific location, just above the hotbed, all the way around at all 4 points around the bed, so that you get a nice even print. And your first layers will start out at the correct thickness. Any change in the surface that you lay this on, you affect the calibration of the bed. So I don't know if you can see this. I'm going to zoom in now. Watch the corner of the bed here as I lift the corner of the frame here. Okay? It's moving. And if the surface that you lay this on is not perfectly flat, then when you calibrate it, you have to find a spot that you're going to leave the printer forever. And that's kind of what I did. I've got little pencil marks on my bench here and at this corner and at the two back corners that I've decided would be the position that I'm going to leave the printer in until I get something else to put it on top of. Now, I could buy a 1/2 inch thick piece of glass that's 18 inches by 18 inches and pay through the nose for it. I think what I'm probably going to end up doing is going to a lumber yard and getting a piece of 1 inch or 1 1/4 inch thick particle board that's been laminated with Formica, and like a section or an unused section of countertop that I could use as a base to set this on top of, so that I can take the whole assembly and move it around wherever I want to. One of the things that you will find in the pre-manufactured units that are for sale in a lot of cases is the whole thing is encased in a rigid frame, and that's one of the drawbacks of an open frame style 3D printer. You just have to be aware of it, so that you know what to expect when you move things around. In keeping with that same train of thought in terms of the Z-axis or the vertical axis accuracy in relation to the bed, one of the things that is required is repeatability when this thing comes down and finds the home switch, so that it knows exactly where it is when you send it to the home position. So the kit is supplied with little micro switches like this. And the problem is that the micro switches are actuated as the gantry comes down and presses on the lever. And there are inaccuracies or repeatability problems with this little micro switch. And what I ended up having to do was replace it with an optical limit switch, and printing up a clamp that holds it to the edge of the vertical Z-axis rail, and then the Z-axis, the motor mount for the Z-axis comes down, and this little aluminum flashing that I bent and mounted to it comes down and breaks the light beam, and the repeatability of that is much, much greater than the mechanical switch that was supplied with the kit. Another situation that I ran into was that the X home limit switch and the Y home limit switch that is at the back corner of the sliding bed assembly set the mechanical home position for the sliding bed in such a way that the nozzle ends up at the extreme lower left-hand corner of the bed on this side right here. So this may or may not be an actual problem. What I have not figured out, and it can probably be offset in the firmware for the controller board in the back, but once it finds the mechanical home, there may be a soft home that I can set. You might be able to constrain it a little bit instead of trying to print all the way to the corners. The reason you don't want it to print all the way to the corners is because the glass that I have sitting on top of here is beveled at the corners, and the nozzle would actually hit the screws that come up through the corners if it utilized the entire surface of the heated bed. So I can't do that. I wanted to constrain the print surface area to something less than the 220 or 215 millimeters square that this thing is. Actually, it's closer to 210, maybe, yeah, 215. So it's 215 millimeters square. The supplier rates the print surface area as 200 by 200, meaning that you've only got a border of 7.5 millimeters all the way around as your print area. But that actually extends into this region here at all four corners, where the print nozzle would be hovering in free space or hitting against the corners. So that was bad. The only way that I found, short of not being able to figure out a way in the firmware to constrain the print surface area, was to actually extend the limit switches out about another 10 millimeters on both the X and the Y, so that the actual mechanical home position is the soft home position as well, and set in the firmware my maximum travel from home to be 180 millimeters. So my actual usable print surface area on this piece of glass right now, unless I dig into it a little bit deeper, and maybe somebody can point me in the right direction where I might change the soft home position, but anyway, my actual usable print area is 180 by 180 by 200 millimeters high. Another problem I ran into is that the original kit design had wing nuts on these bed leveling screws at the bottom. The problem with the wing nuts at the bottom were twofold. First of all, the wing nuts at the back corners of the sliding bed, if they weren't lined up straight back and forth, the wing nuts would actually hit the plastic acrylic frame as the bed moved past it. That was a very big no-no. The other thing was that the wing nuts would come loose by themselves. So what I did to fix the problem, you can see in this picture right here, alright, I eliminated the wing nuts. I put regular nuts on the bottom. I have flat washers on the top and the bottom of the spring assembly to level the bed, and I also put some marine goop, or some goop adhesive, a flexible adhesive, on both the head and the nut, because one of the problems that I ran into was that the vibration of the motors, of the stepper motors, as I was going through a print, was actually causing the screws to loosen up, and the bed would start to raise, and that of course would completely throw off the calibration of the print, because, as I said earlier, Z-axis is probably your most critical adjustment on the printer. Once it finds X and once it finds Y, that's fine. It's a one time per print, and it knows where it's at from that point on. But the Z is absolute. You have to be in the same place every single time, otherwise you will not get consistent prints. So get rid of the wing nuts, put some flexible adhesive on the screws, put some washers on the end of the springs underneath the corners of the heated bed assembly. One of the upgrades that I made to the 3D printer is this piece of plate glass on the sliding hotbed. The original assembly instructions indicate to use masking tape across the top of just the backside of the aluminum plate. I can tell you from experience now that one of the benefits of having the glass plate on top of this is that it's very easy to clean. One of the disadvantages of having this piece of glass on top of the hotbed is that it's very easy to clean, meaning that the PLA does not stick very well to this at all. The recommended temperature for depositing or for heating up the plate is 50 degrees centigrade, but on the glass, 50 degrees centigrade is still too cool to allow the plastic to stick. So I may even go higher than 70 degrees centigrade just to get the PLA to stick to the glass, or I might also try just laying some masking tape across the top of the glass. But the glass was provided to me by my daughter, who works at a framing shop in Litchfield, Connecticut called Ella's Limited, and this is a little plug for Ella. So Heather, thank you for getting me this piece of plate glass and cutting the beveled corners for me, and Ella, thank you for letting her do it. This right here is the Z-axis linear bearing slide assembly. This is the Z-axis linear slide rail, and this is the Z-axis lead screw from the stepper motor. So this is a lead screw, solid lead screw stepper motor, and the way it attaches to the bearing slide is with this flange nut. In the original assembly instructions, you are directed to assemble your screws from the top and then put nuts underneath from the bottom. That would be fine if the flange nut had through holes, but this particular design flange nut has threaded holes. So instead of sending the screws down through the top, tightening them up, and then putting nuts underneath, which is very difficult, I simply opted to use the threads that are already part of the flange nut and take the screws and mount them from underneath. While we're on the topic of flange nuts, one of the things that I really like about this printer was one of the major selling features and one of the major contributing factors to why I bought this particular model is because of the solid lead screw stepper motor that is used in conjunction with the flange nut. This is a upgrade that you will not find in many printers at this price point, and I'm very glad that I purchased a printer with this lead screw design, because I believe that it will provide a much greater service life over the term of the operating life of the printer. Moving to the other Z-axis slide rail, you'll notice that this linear bearing holder is black. That's because I had to replace it. This is the original linear bearing holder that was sold with the kit. Incidentally, all of these plastic parts that come with the kit are 3D printed themselves, and they are reliant on the accuracy of the person who's selling them, on the accuracy of their printers. Well, there was a problem with this particular Z-axis linear bearing holder on the right hand side, and I don't know, it doesn't really show up very well, but this thing is actually the Leaning Tower of Pisa. Okay, it is not square. It is more of a parallelogram than it is a rectangle if you did a cross section. If I set this on my hand like this, it actually leans to your right. And that's bad, because when this assembled to the slide assembly leaned to the right like this, I will exaggerate, that allowed me to only have one linear bearing inside this holder assembly and not two. Otherwise, the whole x-axis gantry would have had to been angled down here like this, and it wouldn't be straight across. So I was either have an unlevel gantry or have it level and only one bearing in there, which made it much less rigid and gave it a lot of play. So fortunately, the supplier gives you the STL files from which to print or reprint all of the pieces that make up the kit. And this one I needed to reprint, and I did, and now life is good. Next up, if you look at this picture, this is the underside of the sliding heated bed assembly, and you'll notice that there are 3 linear bearings that hold the sliding bed to the y-axis rails. So you have one bearing underneath the bed in this location, one bearing here, and one bearing here to give you a 3 points of contact. All right, that's supposed to give you a lot of rigidity on the bed. And there is still, I mean, these are not the world's best linear bearings. There is still a little bit of slop. I'm going to say almost half a millimeter of slop. The way I'm going to get rid of that is I'm simply going to adjust the threaded rods at the front and the back to spread the rails apart just a tiny bit, so that I add a little bit of pretension to the linear bearings and take out that extra slop. I was so careful to get the slide rails so perfectly aligned underneath the bed that I ended up shooting myself in the foot a little bit, and it reveals whatever play is in the bearings. So that should take care of that. On the x-axis, if you look at this photo, all right, here's a photograph of the x-axis with the 2 linear bearings that it was supplied with, and with only 2 linear bearings, I ended up with a lot of rotational slop this way on the print head, as well as rotational slop side to side. And what I ended up doing was adding a 3rd bearing to the lower half of the J bracket that holds the extruder to the x-axis rails, and now that rotational slop in all directions, it's gone. There is no rotational slop. The only movement I get now is the flex of the rails themselves. These are 8mm rails. If I really wanted to make this rigid, I'd probably end up changing all this out and making these 10mm diameter. But for what I'm doing, 8mm is fine. And for a kit like this, 8mm is fine. Let's talk now a little bit about the extruder head wiring and the way it's routed. In the original instructions for the kit, they have you take the wiring coming off of this strain relief on the extruder assembly and just looping it up over the top and down the back, and then lazily connecting it to the controller board that's on the back side of this wall right here. Really lousy design. I decided to emulate the routing of the wires similar to what I saw on the BQ Prusa i3. I forget what the model number is that they give it, but they had a nice little tractor assembly that guided the wires up over the top. But I like the way that it took the whole wire harness and moved it with the X rails. So instead of just looping this wire over the top of the frame and letting it fall where it may, it is now permanently fixed to this motor mount on the left side and allows the X-axis full range of motion like that. And then of course the whole cable assembly moves up and down with the Z travel. The loop comes around the back to the side and then back up to the controller board. So I also have this loop here that allows a full range of motion on the Z-axis up and down. In the original assembly instructions, the fan for the heatsink on the side that keeps the top of the extruder assembly cool was held in place by 3 screws, 2 on the bottom and 1 in the top left closest to the X rails. Now the problem with that is there's nothing behind the screw which extends all the way through to the stepper motor that extrudes the filament. There's nothing to prevent it from crushing this pinch roller assembly in between, other than the fact that the heatsink itself is fairly rigid. But if you tighten it, it would cause it to collapse and close up on the gap here. The solution was to use a shorter screw to hinge the pinch roller assembly and eliminate the top left screw on the fan holding the heatsink to the mount that holds the heated nozzle. In the original assembly instructions, the lower cooling fan that blows cool air over the nozzle as it's printing also had the screw with the screw head on the outside and the nut in the back next to the pinch roller assembly, and there wasn't enough clearance for that. So I ended up having to take the screw, mount it to the J bracket from the opposite direction, put the nut on the outside with a washer underneath to hold this cooling fan in place, and that solved that problem. One other thing to note is that in the very center of this heatsink is a hole that's supposed to be drilled all the way through that should be large enough to give clearance for the gear that is assembled to the shaft of the extruder motor that is pinched, that pinches the filament as it feeds through. It's supposed to be large enough to allow that, but the problem is it's just barely the same size as the gear, and you couldn't extend the gear and adjust the gear on the shaft of the extruder motor properly without over drilling the hole. So I ended up drilling out this hole to wow, I think close to 7/16 of an inch to accommodate the gear and to allow clearance for the gear on the end of the shaft of the extruder motor, and allow this whole thing to go together and have the teeth aligned the way they're supposed to be. Lastly, not critical but certainly an annoyance, some of the threaded screw holes on the flange for the stepper motors were not threaded all the way to the edge of the flange, and the screws, which were just barely long enough to get all the way through the acrylic and into the stepper motors, in a couple of instances the screw wasn't long enough because the threads in the hole started further down, and I couldn't get the threads on the screw once fully seated into the acrylic to bite into the threads of the stepper motor. I actually had to countersink the holes for the heads of the screws on this particular stepper motor in order to get it to mount properly. The other thing is the hole locations for the power supply in the back. Completely off, completely wrong. I had to take the power supply, mount it against the acrylic, and with a Sharpie on the other side try to guess where the opposite side was, and drill out those holes and mount them so that I could get the power supply mounted to the frame the way it's shown in the instructions. Otherwise, you will not mount this power supply. One of the things that I found a little bit disappointing was that the LCD add-on that I purchased on eBay for $15, these run between $15 and $20 on eBay. turns out is not compatible with the Melzi 2.0 board. Yet. I don't know of anyone who has made an adapter for this particular LCD to the Melzi. Maybe it can be done. Maybe that's a challenge I need to issue to the 3D printing community. Can you make this work with a Melzi? There's your challenge. In lieu of that, the only LCD screen or the LCD add-on controller that you can add to the Melzi is a more expensive Painlolu. Strange names they've come up with for all these products. I don't know where they get them, but the Painlolu 2 LCD controller, can't touch those for less than $50, $55 on eBay. And if you want to add an LCD controller to the main board, that's what you need for the Melzi. The benefit of having an LCD is that you can monitor some of the processes in the middle of a print while your computer is disconnected. Really not needed, nice to have, and I may, if I ever get an Arduino Atmega 2560 and the shield for the drivers, which is I think it's called a RAMPS controller, then I'll probably use this with it. Otherwise, I'll just turn around and sell this again on eBay for $15. The total time that I estimate it took to build this kit from start to finish is about 60 man-hours. Roughly 1/3 of that, or 20 hours, was spent assembling the mechanics and doing all of the wiring for the 3D printer. The remaining 40 hours was spent hunting down the correct firmware, learning how to change the settings, figuring out what the correct settings were, calibrating the printer over and over and over, figuring out what I needed to do to get the head positioned and to constrain the size of the print area on the hotbed assembly. Not for the faint-hearted. Having said that, however, now that I've done it once, I could probably do it much quicker the next time. And who knows? Maybe we have a little bit of a cottage industry that's beginning to bloom because of this kit demonstration. Okay? You can get these kits on eBay from Habit Shop for about $350. Finished 3D printers sell for roughly $1,200, $1,300 of this type. Okay? The self-enclosed, all-in-one, latest and greatest, they're still running about $2,000, $2,500. So you spend $350, say it takes you 3 or 4 days to put one together, all right? And then you turn around and sell the completed kit on eBay for anywhere from $700 to $1,000, which is still less than the price of most other fully assembled kits. You've made yourself a nice little chunk of change for that week. Maybe I'll do it myself. Who knows? The last thing that I'd like to mention is the firmware. There is a multitude of various flavors of firmware available for the printer mainboard controllers. Took me quite a while. There's a very steep learning curve in terms of selecting the right firmware, getting the parameters dialed in, calibrating your bed, calibrating your nozzle, the heat, the temperatures, everything associated with the print has to be addressed. And you have to go through the configuration files in the firmware before you upload them to the main controller board one by one to make sure that you've got them all correct. The way the firmware is uploaded to the main controller board is with Arduino software because the processors are essentially Arduino based. This one here, the Melzi 2.0 controller board, is based on the Atmega 1284. The more recent versions of controller boards are typically the Mega 2560s, and that's a more typical looking Arduino board with a shield that sits on top of the Arduino board, and on the shield you've got socket locations for your driver chips and your IOs to the controller board. This one is this Melzi board is an all-in-one board, and it's designed to reduce the cost of the overall controller assembly, and it does a fine job of that. I did have a problem originally getting it to print from the SD card on the main controller board, and I was able to solve that by finding a piece of software that was recommended to me called Pronterface. Not Printerface, Pronterface. And with that software, you can initiate a print that has been saved onto the SD card that's loaded into the slot on the processor board. So the steps of the process are: A, first calibrate the printer. To calibrate the printer, you have to find the right firmware. Finding the right firmware can be a challenge. Uploading it and figuring out how to upload it to the main board can be a challenge. The whole thing was a challenge, really. Then, once you have the controller operating, then you need to create a file. There are a number of ways you can create a print. Either you can download pre-made print files that can be had from websites such as the MakerBot Thingiverse website, which is a very cool website, or you can create your own 3D models in a CAD drawing program. Probably the most popular CAD drawing program in use by the hobbyist is what used to be Google SketchUp, now called Trimble SketchUp, still called SketchUp. They call it SketchUp Make. It's free, and it is an object-oriented 3D modeling program, meaning that you assemble the pieces visually rather than trying to get in and program lines of code to make your models. Another one that seems to be fairly popular is called FreeCAD. FreeCAD is available for Windows and Linux, and it too is free. It too is very, very flexible. It's actually a more powerful program than SketchUp, and also by being more powerful, it is also equally more complex to learn. So I opted to take the simple route and use the SketchUp program instead of FreeCAD. And of course, there are numbers of other CAD design programs that you can use to export your files that could be in a printable format. Once you have your printable object in software, either you've made it yourself or you've downloaded it from a website, once you have that printable file, they can come in a number of different extensions. Then you have to import that file into what's called a slicing program. The slicing program takes that three-dimensional file and it does as the name implies. It slices it into layers and it takes cross sections, and with those layers it guides the print head across the bed to literally draw line by line by line, slice by slice, the object that you've created, and it builds it up higher and higher and higher. It takes a very long time. Some of these objects that you see on the bench next to me took hours to print. Hours. So this is not for high production volumes, but it is for prototyping, and it does a really good job of that. Once you've imported your program or your object into a slicing program, now you need to save it into a machine language that the controller can understand. So the slicing program will now export the sliced file into what's called G-code. G-code is the machine language that the processor understands and interprets and converts those into X, Y, Z positions and extrudes the filament onto your piece so that you end up working and building a 3D piece on your bed. So it's really a three-step process. Create, slice, export to G-code, then you can print. Once you export the G-code, you can print directly from the slicing program, or you can export the G-code to a micro SD card, insert the micro SD card, initiate the print with Pronterface. Once the print has started from the SD card by being initiated from Pronterface, then you can disconnect your computer and leave the printer running by itself autonomously until it finishes the print.
That was easy.
No, not really. Not really. So, why do we go through all of this trouble? What can you do with a 3D printer that would make it worth going through all of that trouble to put one together? Well, here's what you can do. All right, you can make toys, and a lot of people, that's the extent of their creativity. They will make toys. Whoops. Here's a little whistle that I made. So in this picture here, this is this picture that you see in front of you. This is a picture of a bunch of things that I've made recently. This is a little whistle that I downloaded off of Thingiverse. Okay. Yes, it works. It works really well. It's very loud. It's got a little P inside. You can hear it rattle. And it's kind of cool. This little piece right here is a cross section that shows you how it builds up as the print is taking place. Here's a little representation of what I called a combustion engine crankshaft bearing. I drew this up myself from scratch in SketchUp. This little block right here is a little calibration piece that you print and then measure very precisely to make sure that your printer is in calibration. Kind of cool. Have an assortment of little brackets that hold the optical end stops. So I ended up using a particular design end stop over here on the Z-axis for my optical end stop switch. What I ended up doing, what I started by doing, was downloading a bunch of different styles, printing them all up at once. You don't have to print one object at a time. I imported, I think, 5 different designs and printed them all at the same time. And then once all the prints were done, I had a bunch of different little designs that I could select from in order to assemble my limit switch to the Z-axis. And in fact, I will probably end up using one of these or more on my Y-axis if I decide to change that mechanical switch. Here is a bevel gear that I made from scratch. This is part of my magnetic motor project. This is one half of the bevel gear assembly. The other half is a pinion that I'm still working on that will mate to this underneath the rotating magnet assembly. This little gear right here is a miniature version of this. So we have me and we have Mini-Me. It was scaled down 2:1 in the slicing program. So I don't have to create 2 different files. This is the original size, and then in the slicing program I said, okay, I've imported a file of one size, print the next one at 1/2 the original size, and this is what I get. By far, though, the coolest thing that I have printed was last night that I downloaded from Thingiverse because Russ Grease did it and I had to do it better. And took Russ 3 tries to get this print right. This is a dual head, bidirectional, 3/8 inch ratchet wrench printed in one piece overnight. Took about 6 hours to print this. Okay, and then when you're done printing it, if you've done it right, you wrap it on the bench just to break the parts free, because there is supposed to be a little bit of a gap in there, and ideally it's supposed to do that. So I've got a ratchet wrench made out of plastic. I can go through a metal detector at an airport and not set it off with this in my pocket. Isn't that cool? This was actually a design donated to us by NASA, and I guess there was a joke up at the International Space Station where they said, "Hey, we need a wrench," and the ground crew said, "Yeah, we'll email you one." And they're like, "Yeah, right." And it became a joke, I guess, but there it is. Here's the result of the joke. Kind of cool. I don't know that I'll ever use this for anything, but the coolness factor cannot be denied. So, what can I do with this printer that's useful? All right. The first thing that I wanted to print, this is a battery holder. This is a 10 AAA cell battery holder that I want to mount to the wireless microphone receiver that I use for filming these videos on location. Right now I'm plugged into AC power, but when I'm filming on location or recording on location, perhaps doing an interview with a guest, all right, I used to have, and I still do have, this particular battery holder which holds 8 cells. I don't like this so much because the entire top of it is open, and there's no real way to contain the batteries to keep them from falling out. The other thing is I wanted to go from 8 cells to 10 cells. I wanted to go from 12 volts to 15 volts, which gives me a much longer run time on the batteries when I'm out in the field. The only problem is, unlike this particular design, which I was able to Velcro to the back of my receiver, I can't Velcro this because I have batteries on both sides. The solution is I wanted to make a little box for this battery holder that I could slide the battery holder into and have it clip into place, and then the outside edge of the box could have the Velcro that would stick right to the top of my wireless mic receiver, and then I would have what I wanted, a 15 volt power source that I could Velcro to the back of my wireless mic receiver. Perfect application for a 3D printer. I've got some camera mounts that I want to make for the recumbent bike, and doesn't matter what kind of action camera I mount to it, I can print whatever type of bracket I need. You can even print cases for your cell phones. It can be a hard shell case, and there's even filament now called NinjaFlex, and there are some substitutes and some imitation versions of it that will allow you to print something flexible. No, I'm not going to go there. Not going to go there. But you can imagine the kinds of things that you could print with a flexible material. And I'll just let your imagination run wild on that one. But anyway, so there it is. There's my review of the AWorldNet RepRap project. Prusa i3 A600 or H600, still don't know which, 3D printer. If you decide to buy this kit from eBay, I can actually kind of recommend it. If you are a skilled enough builder, yeah, get it. And I will publish for you at altenergy.org all of the final settings in the firmware that took me quite a while to derive, so that you can just load the correct firmware into your printer and get to work a lot sooner than I did. That's all for now. Thank you for watching. As always, please rate, share, comment, and subscribe. And peace, everyone.